Hi, Dr. Tran.
Hey Preston, how's it going?
Um, I'm kind of struggling with homework 2A. I
Okay.
don't know if you could look at it real quick. I got the moment force or like the force at the from the muscle, but
Uh-huh.
getting the force at the joint, I'm kind of struggling. I don't know what I'm doing wrong, if I'm overcomplicating it or
All right, let's see. Let me see if I can find my work for it.
but I can show you what I have right now.
Okay. Yeah, let's go with that. Let me go ahead and stop sharing here. Oops. All right, go for it. Let me see.
Okay, thank you. So I have this right here.
Yep.
So I got the moment or the force from the muscle,
Yep.
but would the J and the X be, I've tried it both ways where it's going along the forearm, or would it be like this and this for,
Yeah, so for this one, I actually did because I use X and Y, I actually did it perfectly horizontally and perfectly vertically. And so
okay.
yeah, so when I sum up the forces in the X direction, I just have JX just by itself, which I think looks like what you have there at the bottom.
Would it be, so I'm kind of confused. So like, would it be, would JX be pointing, it would be pointing this way then?
Yes. Yeah, that's how I have it in this problem.
And so I would have to take I'm confused on how I would get the X component based on F of M then from
Yeah,
here.
yeah. I think the trigonometry I think for this one is
Yeah, that's
probably
kind
the
of
most challenging
throwing me.
part. Yeah. So and so you have two angles here, right? So you have regular
Mhm.
theta and then you have theta M.
Uh-huh.
Um and so the kind of the thing you should do for and let's do FX first because that one's easy
Okay.
because there's no both W and WA don't make any contributions to
Mhm.
some of the force in the X. And so you're gonna have JX that's going to the right, which is what you have, and
Mhm.
then you're gonna have one contribution from FM, and so the FM is gonna be a minus FM,
Uh-huh.
and then it's gonna be a cosine term because the angle was defined with respect to the horizontal,
Uh-huh.
but then the angle that you put inside the cosine is actually going to be theta plus theta m, and to kind of see that, if you because right now it's a little bit hard to see because FM is defined and it's attaching kind of midway up the shaft, right? But
Uh-huh.
for just a moment, if you move FM down to the end of the arm where theta is defined,
Mhm.
just for
Like right there.
illustration purposes, yeah. And so do you see that the total angle with respect to the horizontal that FM makes is going to be theta plus theta m because theta m is defined with respect to the arm, whereas theta is defined with respect to the horizontal. And so,
Oh, okay.
yeah.
And so WA and W wouldn't do anything.
Exactly, right. Yeah, because
Okay.
I think that's the reason why I did, just regular horizontal X and vertical Y, just so that for the X component, W and
Okay.
WA don't mess with it. Yeah.
Okay. Thank you so much.
Yep. Hmm. Yeah, she is. Yeah, thanks for asking. Yeah, she did test negative, but you know, she is still coughing quite a bit. So I've already kind of put in my notice to be out all this week, and so you know, I'm just gonna work from home the rest of the week, and then I should be back by next week. Yeah. Okay, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Good.
Good to hear. All right. So today we're going to be continuing our lecture notes on lower extremity biomechanics, right? And so we have a little bit of the lecture slides left to go. I think we mostly just have to talk about ligaments and the muscles of the lower extremity, and then we're going to start to jump into doing some static analysis. Okay, and so I think that'll take up the entire time today. All right, and so I think that's the yeah, not too much on announcements today. And so are there any questions I can answer before we get started? Okay, all right, so let me go ahead and switch to my laptop. Okay. All right, and so we left off basically right here. Let me go ahead and move to that slide. Okay, and so last time, we left off, we were talking about the lower extremity. Okay, and so we kind of just finished talking about the upper extremity and doing some static analysis on that. And now we're going to be doing the same thing for the lower extremity. Okay, and so if you remember from Monday, the lower extremity is kind of a unique part of your body where it has to be really strong because it's responsible for bearing a lot of the weight of your body, but it also has to be pretty mobile too at the same time, because it's moving your body forward through walking or running or jumping. All of this is provided by the lower extremity, and so it can't really afford just to be really stiff and really strong. It has to have a good range of motion at the same time, right? And so there's a lot of stress that gets put onto the lower body, because of the just naturally from all the weight that it has to bear and from all the powerful muscles that are down there in the lower body as well. Okay. All right, so last time we started talking about, what are the bones and what are the joints in the lower extremity. And so today, we're going to start out by talking about the tendons and the ligaments, and then the muscles. So some more of the soft tissue that we have here in the lower body. Okay. All right, so let's start with the ligaments and tendons. Okay. And in particular for the ligaments, I want to focus a lot on the knee joint, because these, the knee injuries happen quite a bit for a lot of people. They happen a lot for athletes just because of the structure of the knee. But even regular people doing regular things, they experience a lot of knee injuries, because the knee joint is a very unique joint in that in terms of stability, it's not the most stable joint in the world, because what you have on the bottom here, which is the tibia, you have kind of a very flat surface, right? And so just by that nature, just having a really flat bone at a joint is not that stable, because nothing is going to naturally stick to it or cling to it just because it's so flat. Okay, and then on the upper side, or the superior side, we have the femur, which has this kind of dual-headed shape to it right here, where it kind of makes contact on the tibia in 2 different locations, right? And so because of this shape, it's it forms a hinge really well. But compared to a lot of the other joints in the body, the knee relies really strongly on all the ligaments in order for it to have stability. Okay, ligaments and the muscles as well, right? Because the bones by themselves don't provide that much stability based on their shape. All right, and so let's talk about some of the ligaments that we have in the knee. So we'll start with the cruciate ligaments, right? And so the cruciate ligament stands for the ACL, which is the anterior cruciate ligament, and the PCL, which is the posterior cruciate ligament. Okay. And these are 2 ligaments that are that occur on the inside of your knee. Okay, so you can see them from the image right here. They're on the inside, right? And the names of what they get depends on where they attach from, basically. So the anterior one's going to attach on the front, at least the femoral attachments on the front, and the PCL is going to attach on the back, which is called the posterior one. Okay. And so of these 2, ACL injuries tend to be a lot more common, just because of the knee undergoes, a lot of different stresses. And, one particular stress that occurs is the rotation of the knee. Okay. And so if your knee kind of rotates in an awkward way, then this is going to cause your ACL to get injured. And in the worst cases, it can tear. Right. And having a torn ACL is usually pretty terrible, just because the body can't naturally heal the ACL, at least not effectively. And so for a lot of people who get, a really bad ACL injury, they're going to have to get it replaced surgically by another one. And depending on how good the surgeon is, your knee may not ever be the same again after that. Right? I'm not sure if I said this last time, but my dad actually tore his ACL playing pickup basketball in the park. And that happened when he was relatively young. And so he was still in his 40s at the time. And so he had to get it surgically replaced with a new one. But unfortunately, he was just never the same after that. And so he was never able to do the same kind of athletic activities as he was before. He's tried to stay active with, jogging and stuff, but it's it really cut down a lot on the quality of his life once he tore his ACL. Okay, and so those are the ligaments on the inside of the knee. On the outside of the knee, we have what are called the collateral ligaments, right? And so those the MCL and the LCL. And so the MCL stands for the medial collateral ligament. And so this is going to be on the inside of your body. Okay, that's why it's called the medial one. And then the LCL is the lateral collateral ligament, and that attaches on the outside, just like that. Okay. And so these ligaments here, what they're mostly responsible for are preventing lateral motion of the knee, right? And so if you get struck kind of on the outside of your knee, so let's say that you're playing football and someone tackles you at the knees, right? Your knee is going to naturally want to bend inwards, like this, okay? But what prevents that motion are going to be your your MCL and your LCL, right? And in particular, the one between the MCL and the LCL, the one that tends to get injured more is the MCL, okay? Because that prevents your legs from kind of bowing inwards, okay? And if you think about, how people typically hurt these ligaments, a lot of times they're from sustaining some kind of blow from the outside, right? And most blows that come from the outside, they're going to strike the outside of your knee. And so if it strikes the outside of your knee, then it's going to cause it to bow inwards, right? And so that's going to stretch, or that's going to injure your MCL, right? And so you're going to see MCL injuries a lot more commonly than the LCL, just because that inward bowing or that inward bending is a lot more common than being stretched from the inside, okay? All right, and so those are the ligaments in the knee, right? Now let's talk about some of the other soft tissue of the lower extremity. And so probably another one that you've heard a lot is the Achilles tendon, right? And so the Achilles tendon is a kind of a fairly large tendon on the back of your lower leg, okay? And it connects your calf muscles to your heel bone, right? And so basically your Achilles tendon is what gets stretched whenever your calf muscle contracts, right? And so whenever you do any kind of plantar flexion, and so you're planting your foot into the ground, then your calf muscles are contracting. And then the Achilles tendon is what transfers that tension from the calf muscles down to your heel bone. Okay. And so the Achilles tendon is the largest and strongest tendon in the body, okay, because it has to sustain a lot of forces. Okay. But an injury to the Achilles tendon it can be really devastating for people, right? And so there's it happens fairly often in basketball. And so when players tear their Achilles tendon, then they're in for a very long recovery period, right? And so Kobe Bryant, very famously tore his Achilles, and he came back from it. He wasn't really the same after his Achilles injury. More recently, Kevin Durant, if you're familiar with him, he also tore his Achilles, but miraculously for him, it seems like he took an entire year off to heal his Achilles. But when he came back, it seemed like he was just as good as he was before he left, which is pretty amazing. That it usually doesn't happen like that. Okay, and then the last bit of soft tissue that we'll talk about in the lower extremity is the meniscus, right? And so the meniscus you can actually see from this image as well. And so the meniscus kind of acts as kind of like almost like a small cushion in between the inside the knee joint. Okay, because just naturally, due to the types of motions that the knee undergoes, just in terms of weight bearing and and impacts that it sustains, then the femur and the tibia are going to be naturally kind of impacting each other a lot, right? And so if you have a bone-on-bone contact here, where if there was no meniscus, then that can wear down your bones and wear down the joint very, very quickly. And so the meniscus is kind of a piece of soft tissue in between the thigh and your lower leg that kind of cushions these blows and makes it so that you don't wear it down. Okay. And so their main job is to basically transmit the load. Okay? And so whenever there is kind of a compressive impact at the knee, then the meniscus kind of distributes that load effectively. And then through that, it helps with shock absorption. So just to make sure that any big impacts, don't cause any damage. Okay. Okay. Any questions on this? Okay. All right, so let's talk about the muscles of the lower extremity. Okay, and so there's quite a few muscles here in the lower extremity, and they're all fairly big. And so remember, we were talking about the comparison between the upper extremity muscles and the lower extremity. And so the lower extremity muscles are going to be much larger and much more powerful, just because they have a lot more responsibilities and a lot more weight bearing that they have to do. Okay. All right, so let's start with the gluteus muscles, and let's start with the gluteus maximus. And so this is the probably the muscle that people talk about the most on their buttocks, right? And so this is basically this muscle right here that I'm circling with my mouse. Okay. Right. And so this is the muscle that's mostly responsible for hip extension, right? And so whenever you want to kick your leg back, for your entire leg, not just your lower leg, but both your thigh and your lower leg, you want to kick it backwards. Okay. Remember, we call that motion hip extension because we're increasing the angle of the hip joint. Okay. Then the gluteus maximus is the primary muscle that that accounts for that. Okay. And remember, kind of what I've been talking about with muscles, the last few weeks, that if you're curious about what kind of motion the muscle produces in your body, right? A lot of images nowadays will kind of show the muscle fibers kind of going in a certain direction, right? And so what you can do is that, with that in mind, kind of take your hand and say that, if I were to take this, and of course I'm doing this for the butt muscle, but imagine yourself kind of pinching the muscle in that direction, okay? And then, if you're pinching the muscle in that direction, along the same directions as the muscle fibers, then what kind of motion is that going to produce in your leg? Okay. And so you can see here for the gluteus maximus that when we kind of compress the muscle this way, okay, along the muscle fiber direction, it's going to cause the entire leg to kind of rotate backwards like this, right? And so that's what produces the hip extension motion. Right? Okay. All right, so that's the gluteus maximus, and so that's the large muscle on your butt. Okay. Next, we have the gluteus medius. Okay. And so the gluteus medius is this muscle right here. Okay. Right. So it's part of the gluteus muscle group, but it's on the medial side of the group. Okay. And so this is what's responsible for hip abduction. Right. And so once again, if you kind of look at the direction that these muscle fibers are running, if you kind of pinch the muscle like this, okay, you're going to see it's going to want to take the leg. And I think maybe the other side is a little bit easier to see, right? So let's look at the gluteus medius on the other side. Okay. Right. And so if we pinch the muscle this way along the fiber directions, then it's going to want to abduct the entire leg, right? And so the leg is going to go kind of laterally outwards like this. Okay. And so when you do jumping jacks, right? And so when you jumping jacks, you kind of move your arms and legs laterally outwards and inwards. It's the gluteus medius is going to be what's going to kick your leg kind of laterally outwards or to the side. Okay. And so that action, remember, is called hip abduction because you're basically taking your leg and you're moving it away from the body. All right, so next we have the quadriceps, okay? And so the quadriceps muscle group is labeled right here. And so the quadriceps are located on the front of your thigh, okay? All right, and so this is probably one of the more important muscles in the body, okay? Question, so are the gluteus medius, AKA the love handles? So love handles are not muscle tissue, so those are fat. And so fat is usually built or put on top of muscle. But I think, the way people think of love handles, I think they're a little bit above. And so love handles are usually around the gut area, kind of right here. Yeah. So the gluteus medius is a little bit below that. But anyway, you know, any kind of fat tissue that you put on your body, a lot of it goes on top of the muscles, but then also some of the fat goes inside the muscles too. And so you can have your muscles kind of inlaid with fat in here. Okay. And so if you've ever bought like a good steak, you can kind of see that a lot of the fat is kind of built into the muscle. So there is fat that goes through the muscles, generally. But once all of those cavities are filled, then the fat kind of adds itself on top of the muscles. And usually, if you're at the stage where you have love handles, and that's kind of where you're at. Yeah. Okay. Quadriceps muscles. Okay, so these are the muscles on the front of the thigh, and so these are probably one of the more important muscles in your lower leg, because they're responsible for two very important motions that you do on a very regular basis. Even just walking from one location to another. Okay, and so the two motions that it is responsible for is knee extension and hip flexion. Okay. All right, and so once again, let's kind of do our kind of exercise from before. So you can see kind of the fibers running this way, right? And so they kind of run up and down the longitudinal axis of your body, okay? And so if we pinch this muscle, so we kind of take it and we kind of apply a compressive force like that, right? And you do that on your body right now, you can kind of feel naturally that your leg is going to extend, right? And so if you're sitting down in a chair right now and you pinch your quadriceps, then it's going to want to kick your leg outwards like that, right? And so that's knee extension. Right? And so the other action that the quadriceps are responsible for is hip flexion, right? And so on the one hand, your quadriceps attaches down at your knee right here, okay? And so that's what's going to cause the knee extension. But the other place where the quadriceps inserts is actually, and it's a little bit hard to see from this image, but it also attaches onto your hip bone right here as well, okay? And so when you flex this, when you flex the quadriceps muscle, right? Of course, your lower leg is going to want to come outwards like this with extension, okay? But it's also, because of how it attaches onto the hip, it's also going to want to take your entire thigh and kind of bring it up towards your body as well, right? And so almost like a sit-up motion. And so if you're performing a sit-up, part of the muscles that kind of brings your thighs closer to your body are your quadricep muscles, right? Your quadricep muscles and your abdominals kind of both do that, but the quadriceps helps, at least in terms of moving your thigh upwards in hip flexion. Okay. All right, and so that's the quadriceps. Okay. The other major muscle in your thigh are the hamstrings, and so the hamstrings is representing a group of muscles in the lower body, right? And so these are the main muscles of the hamstring, and there are a few more, I think, but these are kind of the major ones. And their main responsibilities, similar to the quadriceps, or I would say opposite to the quadriceps, is going to be knee flexion, okay, and hip extension. Right? And so knee flexion, I think, is pretty easy to see because you can see here that we have this muscle, okay, and the fibers are running this way along the thigh, okay. And so if we pinch this muscle like this, okay, it's going to want to take the knee or the lower leg, and it's going to want to have it rotate upwards towards the body, right? And so that's knee flexion, okay, because you're flexing the joint at the knee, right? And then the other action that it helps with, it actually assists the gluteus maximus in hip extension, right? And so not only is your lower leg going to want to go up that way, but the upper leg, the thigh, is going to want to rotate this way as well, right? Actually, it's a little bit hard to see, so let me go ahead and clear, okay? Right. And so flexing your hamstring muscles is going to want to bring the back of your thigh up towards your butt, okay? And that's called hip extension. All right. And so those are the two major muscles in the thigh. And so the last major muscle that we'll go over, and it's not the last one, you have other muscles too, is your calf muscle, right? And so the calf muscle, it consists of, just like the hamstring, of several different muscles here, okay? but we kind of all group them together into one because they produce, you know, relatively the same motion, all of them. Okay. And so your calf muscle is this, you know, big muscle here on the back side of your foot. Actually, over here, it's a lot easier to see. Okay. And so here is your calf muscle. Okay. Right. And the main responsibility for the calf is for plantar flexion of the ankle, right? And so just like we always do, we can kind of draw lines here for the fiber pattern in the calf. You can go ahead and pinch it like we usually do, okay? Right, and so you can take one of your hands and go to your calf and just pinch it, okay? And when you pinch it, you can kind of see, kind of feel that it's going to want to take your toes and point them, you know, it's going to want to move them closer to the ground, right? And so that's plantar flexion, okay? All right, and just you know, just to kind of refer to the previous slide, you know, we talked about the Achilles tendon. You can't see purple at all. Let me do blue, right? And so this this big piece of white tissue right here, this right here is your Achilles, right? And so your Achilles, once again, it attaches your calf muscle to your heel bone, and so it transfers the force from the calf to the heel, and it's just so that the leg can do plantar flexion. Okay. Any questions on this? Okay. All right. I think that's the last one. Okay. Yeah. So we'll save injuries for later, but let me go ahead and return back to the iPad so we can start doing some static analysis problems. Okay. All right. So let's jump back in here. Right. And so this is going to be static analysis of the lower extremity. All right. And so, you know, when we went over the upper extremity, you know, we introduced this idea of the of static analysis, right? And remember, what we could solve for this, or what we were solving for in these types of problems, is we were solving for how much force the muscles are exerting. Okay. Okay. And so that was one thing that we could solve for in these problems. And the other thing that we can solve for is the magnitude and the direction of the reaction forces at the joints. Okay. All right. And so these are, you know, the main goals of static analysis, because whenever your body is being held in some kind of static position, you know, your muscles have to fire, and there has to be some kind of reaction force at the joints. Otherwise, you know, then your body can't maintain any kind of equilibrium position. Okay. All right, and so we're going to be doing the lower body this week, and so compared to the upper extremity, you know, we'll see the body weight play a much bigger role here. And in fact, actually, with the upper extremity, I don't think we ever used body weight at all. And so we did incorporate the weight of the different parts of the upper extremity, so like the weight of the arms and stuff like that, but not the weight of the entire body. Okay, and so With the lower extremity, you know, obviously this is going to be a lot more important because the lower extremity is what's supporting all your weight. Okay. All right, so let's go ahead and start right off the bat with an example. Okay. Because we're familiar with, you know, what all of this has to do, or how to perform the static analysis. You know, I think we just have to see some examples of it being applied to the lower body. Okay. All right, and so let's consider the hip joint of someone's body. Okay. Okay. And the hip joint in this configuration is going to be simply just supporting a person's weight. All right. All right, and so you know, just to kind of give some context for this, you know, even just standing up straight, you know, your muscles of the muscles of your lower extremity actually have to produce some tension in order to keep your entire body together and to maintain balance. Okay, in particular for the hip, you know, when you're just kind of standing straight up, the natural tendency, just because of the geometry of the thigh bone and the pelvis, the natural tendency is going to want to is for your thighs to kind of rotate outwards. Okay. Okay. You know, just kind of ignore the fact that, you know, we have a very stable, you know, ball and socket at the hip, right? But if the ball and socket at the hip joint wasn't so stable, you know, you kind of have a lever that's kind of tilted slantedly. Okay. So let me go ahead and draw that. Okay. And so that's kind of a representation of your thigh bone, or at least a very crude one. Okay. And then on the other side, on the right side, this is going to be your pelvis. Okay. Right. And so normally, you know, this fitting right here is a lot closer than what I have drawn. And so, you know, just by the natural fact that, you know, this fitting is so tight, then, you know, you're not going to get any rotation outwards. Okay. But because the thigh bone kind of has this kind of inward curve right here, right? And so it's kind of just naturally curving towards the inside of your body. You know, the natural thing for this thigh bone to want to do is kind of rotate outwards like that. Okay, especially when you have the weight of the body that's being acted on the system. Okay. All right, and so let's assume that you know, and of course, you know, we're looking just at one side of the body. But let's assume that we have the weight of the person, you know, being applied in the vertical direction like that. Okay. And then stabilizing this joint, you know, we have a muscle. Okay. And so the muscle that we're going to look at is one of the hip abductors, right? And so this would be the gluteus medius, right? And so we're just going to see a 2D representation of that, right? And so the gluteus medius would kind of attach, you know, kind of like this, right? And then what this is going to do is it's going to apply a force. Okay. Oops, too much. Okay. And so what the gluteus medius is going to do, remember, the gluteus medius is a hip abductor. And so it's going to want to kind of pull the thigh bone that way. Okay. But one way that we can represent that is we can just put a FM like this. Okay. Right. And so if we kind of go back to, you know, how the abductor muscles attach, right? And so it's going to attach on from blue, just like that. Okay. And so this FM is perfectly in line with the fibers of that muscle. All right. And so in addition to FM, We're also going to have a reaction force at the joint, okay? And then for now, we're going to assume that we know this reaction force, or at least the direction of the reaction force, and we'll call that R, okay? All right. Okay, so all the actors are in play, okay? And so if you, in case it's not really
Professor?
that clear. Yeah, what's up?
Oh, can you explain the scenario again? I don't really understand it.
Yeah. So this is the scenario, just someone just standing straight up. And so basically the situation is, someone's kind of standing like this, okay? And then what we're looking at is kind of the hip joint right here. Yeah. And so we're just looking kind of at the upper thigh. And so this bone right here is the femur. And then this bone right here is the pelvis. Yeah. And so the kind of the natural shape, just because of how the thigh bone kind of attaches to the pelvis, it kind of, is kind of bent kind of inwards towards your body. And so the natural tendency is going to be for this thigh bone to kind of rotate outwards like this. But what's going to stop that is going to be the hip abductor muscles right here, FM. Yeah.
Oh, I see. Thank you.
Yep. Mm-hmm. All right. And so the subject of this analysis is actually going to be the pelvis, right? And so that's why I kind of drew the FM muscle attached to the pelvis like that. Okay. Right. And so we're gonna do static analysis on the pelvis right here, okay, and solve for FM and R. Okay. All right. And so in this case, we're going to assume that we know the directions of FM and R. Okay. And so actually for this one, we're not going to need any moment equations. We're only just going to use the force balance equations to solve for FM and R. Okay. Actually, let me go ahead and write in those angles just so that we'll have the next page. Okay. And so if I draw kind of a horizontal line right here for FM, then we'll assume that this angle right here is 70 degrees. Okay. And then for R, we'll draw the horizontal line. We'll assume the angle for the reaction force is 75 degrees. Okay. Any questions on this? Okay. All right. And so since we have the directions for FM and R already, we only need two equations here because the only unknowns here are going to be FM and R.
I'm sorry, Professor, I have a question.
Sure. What's up?
So can you go back a page?
Yep.
So why are we assuming that FM is acting outwards?
Yeah, no, it's a good question because it depends on what the subject of your analysis is or what you're drawing the free body diagram around. And so for this particular problem, we're doing our analysis on the pelvis bone. And so if I kind of draw in the hip abductor muscles again, the hip abductor kind of attaches at two places. And so on their upper attachment, they attach on the pelvis bone just like this. Actually, this it's getting a little bit messy. So actually, let me draw it again over here. Draw it a little bit bigger too. Right, and so this is our pelvis bone. And then this is going to be our thigh bone. Okay. Right. So this right here is our femur. No E. Okay. And so the hip abductor muscle, the gluteus medius, it attaches on one end to the pelvis like this. Okay. And so there's one attachment point there. And then the other attachment point is going to be on the femur right here. Right. And so very roughly, the gluteus medius looks like that. Right. And so when this muscle contracts, right, and so the muscle kind of pulls, produces tension on its own, it's going to pull the pelvis muscle together with the femur because you're going to have one force that gets right here. Okay. And so this force right here acts on pelvis. Okay, because that's where it attaches. Whereas the bottom muscle right here, this is going to act this way. Okay. And this force is going to act on the femur. Right. And so for this particular problem, we're doing our analysis on the pelvis bone, right? And so the muscle force, that's why I put the muscle force kind of in the downwards left direction, because that's the direction that the hip abductors are going to be pulling.
I see. Thank you.
Yep. And that's the other reason why the reaction force, we actually assumed it to be this way as well, right? Okay. Because when the femur and when the pelvis bone are kind of brought in contact with each other, then the femur right here is going to be pushing on the cavity kind of on this location right here. And so that's why the reaction force is up towards the pelvis, because that's the reaction force that the thigh bone places on the pelvis. Okay. If we were to do this analysis on the femur, you know, we'd put everything in the opposite directions. All right. All right, so let's go ahead and write out the force balance equations. And we don't need the moment one here because, you know, we've already kind of assumed the directions for FM and for R. Okay. All right, so let's go ahead and sum the forces in the X direction, okay? And so in the X direction, what we have is the muscle force, okay, minus FM. And we have cosine of the angle. And so the angle, the attachment angle, or at least the angle on which the muscle acts relative to the horizontal is 70 degrees. Okay. Then we have the reaction force. Okay. And this is also going to be a cosine. Okay. But the direction for the muscle force is, or the reaction force is 75 degrees. Yeah. Yeah, it was 70 degrees for the muscle force, and then 75 degrees for the reaction force. Yeah. Mm-hmm. Yeah, they're slightly different directions, just kind of based on the geometry. Okay. All right. All right, so now let's go ahead and sum the forces in the Y direction. And so in the Y direction, we have a minus FM sine 70. Okay. And so this is for the, you know, the muscle force in, you know, the vertical component. Okay. Then we have a plus R sine 75. Okay. And then, you know, it might have gotten erased. Oh, no, it didn't. But then we also have the weight acting in the vertical direction as well. Okay. So we have minus W, and then that's going to be equal to 0. Okay. All right. And so these are the only two equations that we need, because the unknowns in our system here are FM, the muscle force, and R, the reaction force. Okay. And so with two equations and two unknowns, you know, it's not that bad to solve for this. Okay. And so let's go ahead and solve the first equation for FM. Okay. Okay. And so we do that, we get FM is equal to R cosine of 75 divided by cosine of 70. Okay. Right. And then now what we can do is we can take this result and plug it into the Fy equation. Okay. And so we do that, we get minus FM, but we just solve for FM. So FM is going to be minus R cosine of 75 divided by cosine of 70 times sine of 70 plus R sine 75 minus W is equal to 0, right? And so we've eliminated FM from this equation, and so we can just simply solve this straight up for R, right, with a little bit of algebraic, a little more algebraic manipulations. And what you get is R is equal to 1,177.3 newtons. All right. Oh, I never gave you a value for W. And so let's assume that W here is 300 newtons. Okay. So we have a 300 Newton dude or dudette. Okay. 300 Newton person. Okay. All right. And so you can see that, even in this really simple case right here, we have a reaction force here that's much higher than the weight. Okay. All right. And so now that we solve for R, we can go ahead and plug this back in and solve for FM. Okay. And then that'll be it for the first example. All right. Any questions on this so far? Okay. All right. All right, and so if we plug this result for R back in, we can solve for FM. Okay. And what we get for FM is 890.91 newtons. Okay. Right. And so what you'll notice from here is that, if you kind of remember that MW here was 300 newtons. Right. We can see that both the reaction forces and the muscle forces are much higher than the weight of the person. Okay. All right, and remember, we talked about this quite a bit, last time with the upper extremity, right? And so the amount of forces that your muscles have to exert are almost always going to be much higher than any kind of external force that's being applied. And the main reasons for that are, for a lot of times, your muscle forces are not acting in the optimal direction in order to oppose the force, right? And so for this particular case, it would be really optimal if your muscle force was acting just vertically upwards. Then it can just counteract the weight just by itself. Yeah. Oh, question. So can I go over the direction of the resultant force one more time? Yeah. And so for this problem, the direction of the R was just given to you. And so for most problems, you're gonna compute the components first, and so you're gonna compute the X direction component and the Y direction component. But for this one, just because it's a pretty simple example, and I didn't want to spend too much time, I just gave you the direction, right? And so you only had to solve for just the magnitude of that force. So after adding Fx and Fy, you can get R. So remember, R is the joint reaction force, and so that's normally what we solve for, like Jx and Jy, kind of in the upper extremity problems. But here I just kind of lumped them together as R, and I gave you the direction for R. But normally you would solve for Fx and Fy by themselves, and in the next example we will do that. But for this particular one, I just kind of just gave it to you just so we can solve it from just the force balances. Yeah. Mm-hmm. All right. And so remember, the forces that your muscles exert is always going to be higher than any kind of external load. And I'd say there are kind of two main reasons for this. Right? And so the first reason has to do with, a lot of times your muscles are not going to act in a perfect direction to counteract any external forces. Okay. Right. And so that was the main issue with this problem here, right? So we have FM, which was pointed at a 70-degree angle up to the horizontal, whereas the weight was kind of pointed vertically down, okay? And the other main reason that your muscle forces are always going to be higher than your external forces is due to the fact that your muscle forces have a much smaller moment arm, or they attach a lot closer to the joint then most external forces are going to be acting. Okay. Okay. All right, and so for this particular problem, we see that we get a muscle force that's roughly 3 times as high as the weight. Okay, and this is actually, even though we have made up numbers here and we've kind of simplified it, this is actually pretty typical, right? And so for kind of a normal person, just kind of walking down the street. Okay. And so not doing anything, particularly strenuous, just regular walking. Not walking upstairs or anything like that, just, walking in, straight down. Right, so during normal walking, the compressive force at the hip joint can range from anywhere to 2.4 to 2.6 times the body weight. Okay. Okay. All right. And so you can imagine that when you actually put the body through some strenuous exercise, this amount of load is going to go up, right? And so if let's say that maybe you start to run, or maybe you're walking upstairs, or you're walking up a huge incline, okay? Then the compressive forces can actually jump up from anywhere from 4.2 to 8.6 times the body weight. Okay. All right. And so, in this problem, we saw kind of a fairly unlikely hero, because I think when a lot of people think about standing and putting loads on the lower extremity, you don't think that a lot of people don't often think that their gluteus muscles is one of the ones that actually helps with this, but you can see here it plays a big role. Okay, mostly just to prevent any kind of lateral abduction of the thigh, or any kind of separation. Okay. All right. And so in the next example, we're going to consider a case where, someone has an injured hip, right? And so we're going to look at and see, how the static analysis changes if a person were holding a cane instead. Okay, so before we do that, are there any questions on this? Okay. All right, so now let's consider a case. Okay. And in particular, they've hurt their hip, and so their hip abductor muscles don't work as well as they used to. Okay. Okay. And so because of that, this person is going to have trouble walking, and they're going to have trouble standing up. Okay. And so to support himself or support themselves, they've gone ahead and purchased a cane. Okay. Okay. All right. And so, before we jump into that example, let's go ahead and talk a little bit about, we'll talk a little bit about gait, which is, how a person walks, right? Just a little bit, because I don't want to get too much into it, because I might cover more either later in the class, or I know it might be a good subject for the final project as well. Okay, and so generally when a person walks, and so people, you kind of walk kind of one step at a time, right? And so when you walk, you kind of imagine you put one foot down, whereas the other foot's going to be in the air. Okay, and then once that other foot touches down the ground, then your other foot comes into the air. Okay, and so you kind of even though you have two legs, when you're doing a walking motion, most of the time you're going to have just one foot on the ground. Okay. And so actually, if you think about it, when you're walking, most of the time you're actually going to be standing up on one leg. Except most people don't really think about it because they're kind of just in motion. But if you kind of watched, if you're with a friend right now, you can do this after the class. Whereas kind of look at them straight on and have them just walk towards you and kind of watch their legs and see kind of what they're doing, right? Because we're balancing on one foot a lot of the times when we're walking, your foot is going to naturally kind of drift towards the center of your body. Okay. Or in other words, your upper body is going to kind of shift such that the one foot that you have planted is kind of matches up with the midline of the body. And that's mostly just for stability purposes. Okay. Okay. And so to draw kind of an image of that happening, let me draw a, and this is of course very exaggerated. And so let's say that this is your leg right here. Okay. And so this upper segment right here, this is your thigh. This is your lower leg. Okay. And this right down here is your foot. Okay. What your body kind of naturally tends to do when you walk is that it kind of shifts your weight in a certain way such that your foot is kind of right underneath your center of gravity, right? And so if we draw kind of the midline of your body, right? And we kind of draw that down, most of the time it's going to be either right on top of your foot or it's going to be pretty close to the foot for the majority of the stage in which you're walking, okay? Okay. And this is really important for stability because if you didn't do this, then you might topple over to the left or to the right, just from walking, just because you're not able to keep stability. Okay. All right. And so when your body is in this configuration, you have kind of a major force that's being applied on your lower leg, right? And that force has to do with the fact that your foot's on the ground right here. Okay. And so you have a normal force that's being applied up from the ground, just like that. Okay. All right. And so if we imagine that the hip joint is kind of somewhere around here, right? Okay. And so that dot right there is the hip joint. In order to oppose this upward normal force, what your body has to do is that your hip abductor muscles, which are the muscles that we just talked about, have to oppose this normal force. Okay. I should say it opposes the rotation from the normal force on the ground. Right. And so relatively speaking, actually, your hip abductors actually do quite a lot of work when you're just kind of walking around or running around, okay? Because the normal force from the ground is going to want to kind of rotate this entire system, counterclockwise, okay? But the hip abductors, what they're going to do is they're going to provide a opposing moment, okay? And so we'll call this FM, okay? Right, and so opposing this this rotation from the ground, the primary responsibility for that is FM, and that's kind of one of the more important muscles that you have, your gluteus medius, for keeping your balance when you're walking. But I think a lot of people don't think about it because they don't actually feel their gluteus medius actually flexing. Okay. Right, so this force right here is the hip abductors, which again is your gluteus medius. All right, and so let's go back to our situation here. And so, we say that we have a person where they just recently injured their hip abductor muscles. And so what that means is that their hip abductors can't exert the force on their own, to keep a person balanced when they're walking, okay? And so what that's going to tend to do is that, instead of your leg kind of having this kind of configuration right here where it's slanted, it's going to want to instead, make the leg more straightened out like this, okay? Right? And so if your leg is more straightened out, then your hip abductors don't have to work so hard, okay? Okay. The problem with the straightened leg like this is that you're now more likely to topple over because you have your center of mass, and that's off center from your one leg that you're essentially standing on, and so you're just going to topple over in this case. Okay. But what can support you is that if you want to have a more straightened leg when you walk, you can have something that kind of supports you from the other side. Okay. Right. And that's going to be your cane. Right. And so the cane is there just to kind of ease ease the load from walking, right? And so I think when most people think of a cane, they think like, okay, the cane is kind of relieving some of the compressive forces that your leg undergoes, and that's certainly true. But one of the other effects that the cane has is that it kind of helps you keep balance and put your leg in kind of a more favorable position so that your hip basically doesn't have to work as hard. Okay. All right, and so in the next example, we're gonna analyze a case with the hip or a case with the cane. Okay, and so that's going to reduce the amount of load that the leg experiences, and it's going to help straighten it out to a certain extent so that your muscle force isn't working as hard. Okay. All right, any questions on this? Okay. All right. Actually, before we do that, a little bit of a question for you guys. So a little bit of a test your knowledge. And so, for a person whose hip muscles are are compromised, and so they can't rely on their hip abductors to help them keep balance. Should they put the cane on the same side as their injured hip, or should they put it on the opposite side? Right. Remember, the goal here is to relieve the amount of stress or relieve the amount of tension that the hip abductor sustains. Okay. It's a little bit given away from this image here, just because I've kind of drawn the muscles and I've drawn the cane. But actually, if you have someone with an injured hip, then actually they should put the cane on their opposite side, right? And so if their hip is injured on the left, they should use a cane on their right side. And so that will actually help them keep balance a lot more easily, because then that's going to help it so that, you know, when their left leg is on the ground, when it's you know, when it's supporting the weight, then that left leg can actually come out more to the outside, because the cane is on the other side supporting the weight. Okay. And so I think, you know, a lot of people don't really realize this, you know, when they have an injured leg, I think, or an injured hip, I think the tendency for a lot of people is to put the cane on the same side as the injury, because, you know, they think that's what it's supporting it. But for the case where your hip itself is injured, it's actually better to put the cane on the opposite side, because that's going to relieve more of the load from your hip abductors than if it was on the same side. Okay. Okay. All right. So that's a lot of prologue. So let's go ahead and jump into the example now. All right. And so for this example, let's consider a person that's walking with the cane. All right. And so relative to the first example that we did, we're going to have a leg that's going to be much more straightened, although it's not going to be complete. It's not going to be completely straight, and so there's going to be a little bit of bend to it still, although not nearly as much as it was before. Oops. Okay. Right. And so on this side, you know, we have the cane. Right. Okay. And so let's assume that we're dealing with the same person, just so that we can compare the loads from the first example to this one. And so let's say that the weight of this person is 300 newtons. Okay. Right. And then let's assume that you know, that of this 300 newtons, 100 newtons are going to be supported by the cane. So we have a 100 Newton normal force right there. Okay. Whereas the 2/3 of the weight is still going to be supported by the leg. Okay. Right. And so we've reduced our load amount on the leg by you know, by about 1/3. Okay. Okay. And then just like I drew on the previous page, you know, by having the cane, it's gonna move the leg away from the midline of the body. Okay. And so now that we have this configuration here, we're ready to perform our static analysis on the leg. Okay. And remember, the main muscle that we're looking at here are going to be the hip abductor muscles. Okay. And so, you know, and so for this analysis, you know, we're not going to worry about the cane, okay, because the cane's already done its job. And so we're just going to focus just on the leg, okay. And so just like we normally do with static analysis, we're going to compute the muscle force, and we're going to compute the joint reaction forces. Okay.
Professor?
Yeah.
I have a question about this whole setup.
Sure.
So, I mean, from the diagram, like, it looks like the person is taking a step forward.
Correct. Yep.
Why is their midline all the way in front of them like that?
Oh, we're looking at the person head on, like this. And so the person's, it's a little bit hard because I do this kind of wide, but the person's other leg is going to be like right here, but in the air. And so we're kind of looking at a person from straight on, and then their face is kind of like facing you.
Like they're walking toward you?
Exactly. Yeah.
Okay.
Yeah. It's kind of really off balance there, but yeah, but the person's facing towards you. Yeah.
Okay.
Professor?
Yep.
So is actually the walking angle, is this extreme, or are you exaggerating just to show the angles?
It's I'm exaggerating, and so it's definitely not. It's definitely, you know, the gap here is obviously a lot bigger than you know, than it would be for a walking person. But yeah, I just use the width of the iPad.
No, I mean like the angle of the leg angle. Like when you draw the angle of the leg, is
yeah.
it that far inside, or are you just drawing it because
It actually is, yeah. It actually does. It still kind of has this tilt right here, and so this angle, maybe not the distance to the midline. So this distance here is kind of exaggerated, but the tilt here is actually, you know, it's not too far from what it is in reality. Because if you kind of compare it to our first example, right? The first example, the tilt was pretty extreme. Of course, this diagram is really messy now. You know, but the tilt was, you know, kind of like what it is right here for this drawing right here. And so we're talking
extreme one.
Yeah. And so this actually is not that much exaggerated, because it's, if you think about, you know, when you're walking and you're at the stage where one foot is firmly on the ground and the other foot's in the air, right? There's actually is kind of an angle from, if you go from your hips down to where your foot is, then there's kind of that angle like it is there. And so having the cane will reduce that, and so it'll make it more straight, but it's not going to be as big as it was before.
Oh, I've never noticed that.
Yeah.
Now I'll look for it.
Yeah, definitely. It's really interesting. So, and you know, I think I think where you kind of see this most pronounced is that if you actually watch like a fashion show and you watch kind of the models walk down the runway, you know, they kind of exaggerate it too much just because they have to make the clothes look good. But you know, that's kind of the motion that people naturally do. It's just that they exaggerate it a lot just to make their hips sway and then make the clothes look good. But you know, everyone does that to some extent, just not to the extent that that runway models do. Yeah.
Okay, thank you.
Mm-hmm. Yeah, and actually, yeah, Jesse had made a great comment. So if you stand with one foot in front of the other, you can see how angled your leg is while walking. Yeah, it actually is pretty extreme. It was surprising for me too when I first saw it, because I think you don't really think about it, because you always think that your legs are kind of always straight up and down, but when you're walking, you know, there's actually moments where, you know, you have that kind of tilt. Yeah. All right. And so let's again just focus on the leg, okay? And unfortunately, this diagram here is going to be a little bit messy, but let me go ahead and do my best. Okay. All right, so let's go ahead and do this. So for this diagram, I'm again going to exaggerate this, you know, for the cane walking, right? And so for walking with the cane, you're not going to have this much an angle, but just so that the figure is not so clumped together, I'm going to try to exaggerate this as much as possible. Okay. All right. And so let's assume that your actual joint is up here. Okay. 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 And so this point right here that I drew kind of at the elbow here, this is where the hip abductor is going to act. And so let's say that we have, let me go ahead and clear some of this just to give myself more room. Right. And so let's say that this this force right here, this is the muscle force. Okay. Right. And then let's say that relative to the horizontal, this theta right here, theta m, we'll say that theta m is 70 degrees, okay? And this is with respect to the horizontal. Okay? So this is a little bit different than what we normally do, because normally when we talk about attachment angles, it's usually with respect to the limb on which it attached to. But because the hip abductor kind of attaches at kind of a weird location on the femur, measuring that angle relative to the femur is actually not that. Usually, it actually doesn't make that much sense. And so we're going to measure that angle with respect to the horizontal. Okay. All right. And then this distance right here, okay, the horizontal distance between the hip abductor and the joint, we'll call this LM. Okay. And let's say that LM here is 7 centimeters. Okay. All right. And so just so that you have a point of reference, you know, let's say that this green line right here is the midline. Okay. And so remember, the hip joint is actually going to be, you know, towards the outside of the midline. Okay, but we're doing all of our analysis with respect to the hip joint. Okay. All right, and so that's FM. Let me go ahead and draw the normal force from the ground. Okay, and so from the ground we have an upward force of 200 newtons. Okay, so that's what we declared before. And if we draw kind of this vertical line from the hip joint, okay, then we can say that the horizontal distance between the normal force and the hip joint, we'll call this LF. Yeah, LF. Okay.
Can you scroll down a little bit, Professor?
Oh, scroll down.
Yeah, the drawing is kind of cut off.
Okay, let me actually let me move this upward a little bit. Okay, so that force there is 200 newtons. And then let's say that this distance right here, this one's going to be LF. Okay. And let's say LF, this is equal to 5 centimeters. Okay. All right. And then we also, in this problem, we're also going to have the weight of the leg. Okay. Okay. And so the weight of the leg is like that. Okay. And let's say that the weight of the leg here is 50 newtons. Okay. And then it's going to act a horizontal distance of LL. And unfortunately, I did kind of a really poor job drawing this to scale. Even in the lecture notes, I kind of drew it poorly to scale. Right? And so LL here is going to be 6.5 centimeters. Okay. And so it's only very slightly closer to the hip joint than the hip abductor muscles, but farther away from the foot. And so, you know, the foot's actually a lot closer to the hip joint than what I drew here. Okay. All right. And then, oh, one other quantity here that I didn't mention. Okay. Let's say that this vertical distance right here, we'll call this HM. Okay. And so that's the vertical distance between the hip abductor muscles and the hip joint. And we'll say that this is 1 centimeter. All right, so a little bit of a messy figure, I know, but it's you know, this figure is also in the notes, and then you can kind of see from there. But essentially, you know, we have three external forces here, and so we have the muscle force, we have the weight of the leg, and we have the normal force from the ground. Okay, so that's the 200 newtons. Okay. And then the other forces that we have here are the reaction forces of the joint. And so we have a JY, okay, and a JX right here. Okay. All right. And so just like we always do, we're going to solve for FM, JY, and JX, okay, based on the geometry of this figure. Okay. Okay. Any questions on the setup for this problem? Yeah, I know the figure's messy, so I think probably on Monday we'll kind of restart with this example, and I'll draw kind of a better figure for this, so just so that you can have it in your notes. But we are almost out of time, but I do want to just do the sum of the forces in the X direction, just because that one's really quick. Okay, so let's go ahead and do that. All right, so in the X direction, we only have 2 forces that are present, okay? Because both the weight of the leg and the normal force from the ground are vertical forces. Okay, and so acting in the positive X direction, we have FM cosine of 70, okay? And since that 70 degrees was defined relative to the horizontal, that's the only thing that we need, Okay. And then the other force in the x direction is the joint reaction force, which is Jx. Okay. And then we sum those together, and then we get 0 from that. Okay. All right. And so we're just about out of time. And so I apologize. We're kind of stopping this example in the middle, but on Monday we're going to pick it up with this example again, and then kind of take it from there. Okay. All right. Any final questions this week before we wrap it up? Okay. All right. So that's all we have time for today. So thank you everyone for tuning in. Thank you everyone for being flexible again today and meeting virtually. And so the plan for next week is to start to meet back in person. So I should be on campus again on Monday. And so for those of you who want to come to the lectures, I'll be in the lecture room. Okay? So have a great weekend, everyone. Hope everyone enjoys the rest of their evening, and I will see you next week.
Thank you, Professor.
Thanks, guys.